The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Now for a different, entirely different type of issue that has more to do with recognition, some psychophysics, some computer vision, but you will see at the end the motivation was really to be able to recognize and understand really complicated things that are happening in natural images. Now when we look at objects in the world, people have worked a lot on object recognition, and we can recognize well complete objects, but we can also recognize very limited configuration of objects. So we are very good at using limited information, if this is what's available, in order to recognize what's in there. And this is some arbitrary collection. I guess you can recognize all of them. Some of them, if you think about a person or even a face, this is a very small part of a face. Everybody, I guess, knows what it is, right? It's not even a recognizable, well-delineated part like an eye. You see a part of a person here, we know what it is, right? We don't, I mean, everybody recognizes this and so on. Now, I think that the ability to be able to get all the information out, even from a limited region, plays an important role in understanding images. And let me motivate it by one example. I'll go back to it at the end. When we look at these images, we know what's happening. We know what the action here is. All the people are performing the same action. They're all drinking, even drinking from a bottle, right? But the images as images are very different. If you look at each image, if you stored one image and you try to recognize another image based on the first one, it will be difficult. The variability here can be huge. But if you focus on where the action really takes place, the most informative part where most of the answer is already given to you of what's happening here, which is where the bottle is docked into the mouth, you can see that now these diverse images becomes virtually almost a copy of one another, right? They're almost the same. So if you manage to understand this and extract the most informative part, and although it's limited and so on, the variability will be much, much reduced. The variability here is much, much reduced compared to variability that you have in the entire image. So most of the other stuff is much less relevant, but this is where the information is concentrated, and in the limited, restricted configuration, recognition will be much easier and will generalize much better from one situation to another because of this principle of highly reduced variability in the limited image. So we became interested, as I say, as you see, it's useful, but it's also to deal with small images and still recognize them, or limited images. You'll see it's much more, there are some very challenging issues. And I want to discuss it a little bit and then also discuss what it's good for a little bit more. I will show you some human studies. What we wanted to see is what are the sort of the minimal images that people can still recognize. We examined some computational models, and I will give you sort of, will not keep the secret. It turns out that well-performing current schemes, including deep networks, cannot deal well with such minimal images. And from this, I want to discuss some implications in terms of representations in our system, brain processing, and things like this. And quite a number of people have been involved in this. Here are the names. Some of them are at the Weizmann Institute in Israel, and a few, Laila is here, Laila Isaac, she's here in the summer school, and a student, Yena Han, at MIT doing some brain imaging on this, which I will mention very, very briefly. So I'll start with the human study. We're looking for minimal sort of atomic things in recognition, and the experiment goes like this. You show a subject an image and ask them to recognize it. Just produce a label. So this is a dog. If they say a dog, they recognized it. And if they recognized it correctly, we generate 5 descendants from this initial image. If this image was, say, 50 by 50 pixels, and tell you about pixels in a minute, but say it's 50 by 50 pixels, we make it somewhat smaller. We reduce it because it's still not minimal, and we reduce it in 5 ways. We either crop it at one of the 4 corners to create, say, a 48 by 48 image by taking 2 pixels from this corner here or this corner here and so on, so 4 descendants. And we also take the full image, keep it as is, we do not crop it, we just reduce the resolution. So we resample it, so some details start to become lost. Instead of 50 by 50 pixel, it's also full image, but 48 by 48. And then we give each one of these images, now we have 5, we give each one, this is beginning to expand as a tree, each one of the 5 is given again to a subject. If they recognize it, again, 5 descendants are being generated, and we explore the entire tree until we find all the sub-images which are minimal and can be recognizable in this original configuration. Now, this is challenging psychophysically in terms of number of subjects because we use a subject only once. Because if you show a subject this and he recognizes it, if you show him the same subject a reduced image, he will recognize the image based on his previous exposure, so you do not want to use him again, so you don't use him again and you show the other images to new subjects. And this requires a large number of subjects, so 15,000 subjects participated in this experiment online by Mechanical Turk, together with some laboratory controls to see that they are doing the right thing and how it compares with the same experiment done under laboratory conditions and so on. So the way we define the minimal image for recognition is in this tree, here is an image. The image, suppose this image is recognizable, and then we create the 5 descendants, and none of the descendants is recognizable. So this is recognizable, nothing here is recognizable. So it's minimal because you can no longer reduce it either by resolution going here or by reducing the size. Any manipulation like this, we make it unrecognizable. Technically, when I'm measuring, if I'm using numbers that the image is 50 pixels or 35 pixels and so on, it's actually well defined. I mean not the pixels on the screen. You can take the image and make it bigger or smaller on the screen, but the number of sampling points in the image is well defined. When you give me an image, a particular image, I can tell you how many sample points you need in order to capture this image. Technically, for those of you who know it, it's twice if you do a Fourier transform and take twice the cutoff frequency, the highest frequency in the Fourier spectrum. This is by the sampling theorem of Shannon. This is the number of points you need in order to. So when I say that the image was 35 pixels, I don't really care. You can make it somewhat smaller or larger on the screen by interpolation. It doesn't change the information content. It's well-defined notion mathematically how many points are in these discrete points or sampling points are in these images. So a very interesting thing that we found when we found these minimal images is that there is a sharp transition when you get to the level of the minimal images. So you go down and you recognize it, and then there is a sharp transition that it suddenly becomes unrecognizable, basically to the large majority of people. So it can change a little bit, and I'll show you some examples for you to try to see how these minimal images look like at the recognizable level, at the unrecognizable. This is the recognizable level, this is the unrecognizable level. So to show it to you as examples here, so I will show you first the unrecognizable one, the one which people find on average more difficult to recognize. And if you recognize it, raise your hand, don't say what you see because this will influence other people, just raise your hand if you recognize the image. And then I'll show you the more recognizable one, and let's see if more hands show up, if the distinction between the recognizable and unrecognizable holds here. I'll just show you a couple of examples from the, okay, so this is the one which is supposed to be difficult to recognize. If you see what it is, if you know what's the object, raise your hand. Okay, don't say what it is. We have two. Let's see here. Okay, certainly more hand. What do you see? What do you think?
Should I say?
Okay, now you can say because a horse, right. So let me show them side by side. So you see that it's very difficult to recognize. It was not recognized. This is, you can see the statistic. This is recognized by 93% of the subjects. 30 subjects saw each one of these images. 93 recognized this, 3% recognized this. And you look at the image and you see that there are very, very similar images, and it drops from 90 to 3%. So you can see the two images, and you can see the similarity, and you can see the large drop. This is part of the entire tree which is being explored. This is the father, this is the recognized one, the minimal image. And you can see that even reduce the resolution, which is really not a big manipulation, but this is a drop in performance, and you can see all the, so we used 50% as our criterion, so the parent should be recognized at higher, this should be recognized at lower, but typically the jump is very sharp. Let's try two more or something, and then just for fun. If you can recognize it, raise your hand. Okay, let's try nobody, just for the record. Okay, look around, you can see many. What do you see? A boat, right. So you can see the two images, so 80% on this, 0% here. And you can see that what's really missing here is the tip here. And clearly this tip is, there are many contours in this image, but this particular corner sharp makes an enormous difference, and it goes from 80% to 0%. Okay, let me skip. Just one more, and okay, let me skip this. This is somewhat easier. Okay, this is some okay, at least one, two, maybe three. Okay, how about this one? Everybody, I think, or maybe we are missing one. So again, you can see that the difference, if you look at the two, there is a difference, and it's this thing here, but it's not a very big part of the image. It's crucial, you know. It's you have to be trained on this. It's part of your representation. It's important. You go from almost 90% to 15% roughly, and it's important. So you can see that the drop is typically very, very sharp, and it's also, you know, the sharp transition is also interesting in the sense that if it drops from like the whole from 90% to 10 to 3%, or even here, it also says that we all carry around in our head a very similar representation, because if each one of us, based on the history and visual experience, would be less or more sensitive to various features, then we will not find this sharp transition. Different people will lose it at different points in the manipulation, but at 90% of the people, roughly everybody recognize it. You remove a feature and it goes to 3%, so everybody is using the same or very similar representation, which I find somewhat surprising, at least for some of these images. You know, that we don't all have the same kind of experience with horses or with battleships or things like that, and still the representation is very strikingly similar across individuals. The experiment was done on 10 different objects. These are the initial objects. So I showed you the objects are at the beginning of the hierarchy, and then you start the manipulation to discover all the minimal images inside them. And here, so we ended up with a very nice catalog. We have a database of all the minimal images in all of these 10 images, and all of the children, the unrecognizable ones. So in terms of modeling and in terms of exploring visual features and what is necessary in order to recognize and so on, there is a very rich data set here of all the minimal images in all of these 10 images. Here are some more pairs of recognizable and unrecognizable. Okay, we already saw this in principle, but just to show some, in some cases it's pretty clear what may be going on. For example, this is horse legs, the front legs of the horse. This seems to be important. You can see that very often it's tremendously small in this fly image, very small differences, very hard to pinpoint, and it's drastic, or in the eyeglasses, something here is missing a little bit, but very small things in very reliable way cause this dramatic change. As was mentioned here, somebody mentioned, let's say, the inflection in point. You can manipulate psychophysically a bit more. For example, here, this is another version of a minimal image. It was cropped at two locations. You can crop only the left side, or you can crop only the bottom side, and you can try to see what makes a difference. So you can really zoom in on the critical features. In terms of number of pixels, the impression is that it's surprisingly small. So I guess you can recognize that this is an eagle, this is an airplane, and the number of pixels. You know, your retina, you know, those of you who know vision, your retina has 120 million pixels. The fovea, which is the area of very high acuity, is 2 degrees. It's about 250 by 250, 250 by 200 pixels. This is the area, the central area of high acuity. But you can recognize things with, I don't know, 15, 20 pixels. It's 1/10 of your fovea. It's tiny in terms of, you can make it larger, but in terms of how much visual information, it's, I find it surprising that you need very, very little. It's also interesting that it's very useful in the sense that it's very redundant. If you have the capacity, if you have a visual system that can recognize individually each one of these minimal images, and in fact they can be recognized on their own, then a full image like this contains a high number of partially overlapping minimal images. Some of them are large. You can see each one of these colored frame is a minimal image shown not necessarily at the right resolution. You can reduce the resolution of things. But you can see that some images are essentially low resolution representations of the entire object, like almost the entire eagle, but some of them just contain something relatively small around the head and the eye. For the eye region, you can see that you can get a low resolution again thing of almost everything, but you can just the corner of the eye and things like that are enough. We find in general, it seems that things that are related to humans, you have a large number of these minimal images. So they provide a sensitive tool to compare representations to see what's missing in the sub-image, which made the image become unrecognizable. So we call them sometimes this acronym, minimal recognizable configuration. We call them configuration, but not images, not parts, or not objects, because they're not objects, and not parts because, as we saw in the examples, they do not have to be well-delineated parts. They are more like local configuration. But anyway, minimal images. The next thing that we did is we were wondering if this kind of behavior, that the ability to recognize this these images from such minimal information requires, it places an interesting challenge or an interesting test of a recognition system, because you really have to extract and use all the available information. By definition, this is minimal. If you do not use all the information that's in this minimal image, then you don't have the minimal information. You have less than that, and you will fail. So a system that is not good enough will fail on these minimal images, or the ability to recognize them means that you really can suck out all the relevant information out. So we were wondering what will happen if we show it to various computational algorithms that perform well on full images. What will happen when you challenge them with things which are by nature designed to be non-redundant? So here is, I will do it, it's not a computer vision school. I will not go too much through the details of the computational schemes, but just to show you what was happening. And the bottom line is that they are not doing a good job. Two things happen. First of all, when you train a computational system, you do not see the same drop that you see here, that it recognizes one and doesn't recognize the other. You don't have a drop in recognition. This sort of phase transition that characterizes the human visual system is not reproduced in any of the current recognition systems, including deep network and any other ones. And secondly, they are not very good at recognizing them. Regardless of the gap that there is a sharp transition or not, they do not get good recognition results on these minimal images. They do not suck all the necessary information. So in the full images, it's like we had an image of a side view of a plane, so we are training on airplane. You can think about deep network. We actually tried a whole range of good classifiers, and in all of these good classifiers, those of you who are not in vision probably got enough at the beginning of this summer school that they have a feeling for a classifier in computer vision. It's a system that, algorithm, a system, a scheme, that you give it training images. You don't have to specify, you don't tell it what to look for. You just give it lots of images and tell them all these are of the same class. And then it calibrates itself and adjusts parameters and so on. And then you give it new images, and the system is supposed to tell you if it's a new member of the same class or not. So in this case, we trained the system giving them full side views of airplane, but then we gave them just the tails compared to random patches taken from non-images. The question is, do they reliably can tell you that this is a tail of an airplane, part of the previous class, or they will be confused and they will give even higher score to things which do not come from airplane at all. We started this when deep networks were still not the leaders, and we had some other things like DPM, and including HMAX, which is a very good model of the human visual system and performs very well. And so we included it as well, and deep network as well. This is the HMAX, this is convolutional neural networks. You probably got the idea, it's just worth pointing. I find it interesting in the computer vision community that it's you have Olympic Games every year. It's something which is very structured and very competitive and very nice in this regard. That there is the Pascal challenge and the ImageNet challenge, and it's well run. And people who think that they have a better algorithm than others can submit an entry, can submit an algorithm. Everybody gets training images. They are distributed publicly, but there are secret images used for testing, and you can train your algorithm on the available data. Everybody uses the same data, and then you submit your algorithm, and the algorithm is run by the central committee on the test images, and the results are published, and everybody knows who is number one, who is number two. You have a gold medal and a silver medal, and it's very competitive, and it's in some sense it's doing very good things. It's sort of driving the performance up. It also has some negative effects on the, I think, on the way things are being done. One negative is it's very difficult to come up with an entirely new scheme which explores a completely new idea, because initially, before you fine-tune it, it will not be at the level of the high-performing winners, and until it establishes itself as a winner, it will not get credit. So it sort of becomes a little bit conservative in this regard, which is the unfortunate part. So as I told you, and I will not go in great detail, the two basic outcomes is that the gap between the recognizable and unrecognizable, these two bars are the gap for human vision, that a whole group of horse images, the parents are highly recognizable, the children, the offspring are not recognizable, very large drop. This drop is not recaptured in this model, in any of the model. If you have a deep network or you have one of these classifiers, what is recognized and not recognized depend on the threshold. You can decide that it gives you a number and it says that I have this and this confidence that this is belongs to the class. So what we did here is that we try to match. We had a class of images and people recognize them at 80% recognition. So we put the threshold in the computer vision system at such a level that it recognizes correctly 80% of the minimal images. So you match them, and then we looked at how many of the sub-images it passed the threshold, and you get, this is for deep network, that instead of a gap, you actually got anti-gap. It actually recognized a few more. But this should not confuse you. It does not mean that the deep network did better than humans. It actually did much worse than humans, although the bars here are higher. And there is the following. You can always, even in a very bad classifier, you can get 80% recognition by just lowering the threshold, and then 80% of the class examples will exceed the threshold. The question is how many just garbage image, non-class images will also pass the threshold at the same time. If you get 80% of the class, but also lots and lots and lots of completely false positive, negative images, non-class images are also saying I'm an airplane, then that's bad performance. So just these high bars do not say anything. The actual recognition levels were very low. We can see here for deep networks that this high bar is the performance on new airplanes. So for airplanes, it did very well. But the percent correct that it did on minimal images were 3% or 4%, so very, very, very low. So it did very bad recognition on the minimal images. So recognition of minimal images does not emerge by training any of the existing models that I know in the world, including not the deep network models. Now, the second test was, as was asked here, is that we did another large test. All of these things actually were a lot of effort and time consuming, because now we have this. This was in the original test, was a minimal image. I don't know, this was a minimal image. Then we collected a range of tails of planes like this for many other airplanes, and we run another Turk experiment, which was pretty large, because we wanted to verify that each one of these patches that we added to our test, and we were going to use for testing recognition, was indeed a minimal image for recognition. So each one of these patches, and there were 60 of those, we ran on psychophysically, and we saw that it's recognizable, and if you make it small, if you try to reduce it, it's unrecognizable. So each one of these is individually also a minimal image. So here we did training and testing on, so this is some examples of this. So here are various images of fly, and each one of them was tested on 30 subjects on the mechanical Turk. And the results are that in terms of correct recognition, there is a substantial improvement from 3% to 60%. But 60% is not very large. People recognize them, I should say, you should look at the false alarm. The number of errors, I will show you later, the number of errors that even after training on minimal images, the number of, the performance of the deep network and all the other models on the minimal images is far worse than human recognition level, human performance on the same images. So it's not just the gap is not reproduced. Even training with minimal images, the performance is not reproduced. The errors or the accuracy is far worse in all the models, including deep network, compared to human vision. So these systems do not do it. It remains to be, you can always ask what happened if I trained it with 100,000 images and I add and add more and more examples. This we couldn't, this becomes more and larger. But with the experiments we've done, which are quite extensive, it does not begin to approach human accuracy. Humans are much better. And I'll show you, I think it's not just a competition, who does better. I think there is something deeper there, and that's what I want to go next. Let me skip some. These are the error comparison, and you can see just to show in a lot of different examples, zero errors for humans, 17% errors in the deep networks, and so on. So there's big differences. Okay, a related thing, which I think gets to the heart of what's going on, that humans can do with these minimal images and model at the moment cannot, is that we not only recognize these images and say this is a man, this is an eagle, this is a horse. Once we recognize it, although the image itself is sort of atomic in the sense that you reduce it and recognition goes away, but once we recognize it, we can recognize sort of subatomic particles. We can recognize things inside it. So if this is a person, we asked again in the psychophysical test to tell us what you see inside the image using various methodologies, which I'll not go into. But people recognize this. This is a person in a tie and suit, for those of you who could not recognize it. But once people recognize it, they say this is the neck of the person, this is the tie, this is the knot of the tie, this is part of the jacket, and so on and so forth. I mean, they recognize a whole lot of details, semantic, internal details inside. If they see this is the horse, sorry, the contrast is low, but they see the ear and the other ear and the eye and the mouth. But if you reduce the image, they lose the recognition completely. Once they recognize it, they recognize a whole lot of structure inside. And I think that the structure by itself is the more interesting part, because when we don't want to say a horse, we don't want to see a car. We want to know where the car door is, where the knob is. We want to recognize all the internal details. But the ability to recognize all of these internal details is automatically, it's also helping you with improving the recognition and rejecting sort of false detections, because these are images that deep network thought that are good images of a man in a suit. But once you dive inside and you say, where exactly is the neck and where exactly is the tie and is it the right structure that I expect, the answer is that it's not quite appropriate, and you can use that so that this internal interpretation is, first of all, the more important goal of vision, but in addition, once you do it, you can reject things that appeared based on the coarser structure to be correct, and in this way you can get the correct recognition, and for this reason, my prediction is that it will be very difficult to get it with current deep network, because what you need is not only to get the label out, but to be able to dive down and get the correct interpretation and inspect it, and it has some properties, what the tie, the knot in the tie is slightly wider than the part under it, and so on. So you have to check for you know these things, and you check for them, and if you don't do it, then the recognition will remain limited. Now, when you look at it and you say, okay, and we try to develop algorithm which will actually dive in and will do the internal interpretation and will do them correctly and will reject false alarms and so on, it turns out that this is an interesting business. You have to be very accurate, and some of the properties and relations that you need to extract are very specific to certain categories and are very precise. For example, this was selected by Deep Network as a very good example of a horse head. And it's basically the right, it does have the right shape. But for example, people reject it. We asked, people did not accept it as a horse head. And they said, for example, that these lines are too straight. It looks like a man-made part rather than a part of a real animal. That was a repeating answer, for example. But deviation, how straight is it, and so on, this is a bit tricky. And also, it didn't have quite the ear that you do expect here. So we think that the kind of feature that you need in order to do this internal interpretation of interest depends on relatively complicated properties and relations that you don't want to spend time and effort doing in a bottom-up way all over the entire visual field. If certain two contours move smoothly or in a corner, or if something is really straight or only semi-straight, I mean, to do all of these computations, my hunch is to do all of these complicated things, you need them only in a small, you need some specific ones for some specific classes at some specific locations. So the right way to do this kind of computation, the right architecture seems to me a combination of bottom-up and top-down processing, and we know that in the visual system, this is a diagram of the visual system which is supposed to show that we have lots of connections going up, but also a lot of connections going down. And the suggestion that I would like to put up, and I think it's what's happening here is that we have something like deep network that does an initial generic classification. It's bottom up, it has some kind of, it was trained on many categories. It is not sensitive to all of these small and informative things that you need for internal classification. And it proposes a lot of, it gives you initial recognition, which is okay. It's especially okay when you have a complete object and not something challenging like a minimal image, because you may be wrong on a couple of the minimal images, but you have 20 of them in each object, so if 2 are wrong, it's not too bad. So under many circumstances, you'll be okay in terms of general recognition, but what this does is it doesn't complete the process, but it sort of triggers the application of something which is much more class specific, that it says, oh, it looks like a horse, let's check if it has, so let's now complete the interpretation. It's not just a validation, but you really want to know where is the eye, where is the ear, where is the mouth, and so on. You want to know maybe if the mouth is open or closed. You want to feed the horse, you want to pet the horse. I mean, when you interact with object, all of these things are important. So you continue your understanding of the visual scene, but this is not this generic bottom-up recognition, but you are looking for specific structures that you learned about when you interacted with these objects before, and then you test specific things. I mean, where is the eye? This should be a round thing roughly here, and so on and so forth. So these are more extended routines that you are applying to the detected region, sort of directed from above, and you know what kind of feature to look for at different locations within the minimal image. And this kind of ongoing, continuing interpretation is not just inside internally to what you succeeded to recognize, but start to spread over the entire image. For example, if you look at this image, what do you see here in this image here? Anyone want to suggest what we see here? Sorry? Woman's face. What is the woman doing? Drinking. Right. So it's a woman drinking. For those of you who managed to recognize, this is the woman. She's drinking from a cup. Now we tested it. The woman is actually a minimal image. It's if you remove the cup, you show this image, people recognize it at a relatively high. Nobody recognizes this as a glass when you just show the glass on its own. We think that you start the actual recognition process in your head starts with recognizing what is recognizable on its own, sort of the minimal configuration, which you know what it is. You don't need help, you don't need context, you don't need anything. This is a woman, this is the mouth, and you can continue from there in the same way that you can recognize internally that this is the nose and the nostril, and this is the upper lip and lower lip. You can, in the same way that you can guide your interpretation process internally, you can also say that the thing which is docked at her mouth is a glass. Some results from this has been implemented by Guy Ben Yosef, who is also now a part of CBMM, and this internal interpretation begins to work interestingly well. We started to do at MIT some MEG studies, because if this is correct, if the interpretation process and the correct recognition of minimal images and the following full interpretation process is driven by, or it requires, for completion, it requires the triggering of top-down processing, that we could see it in using the right kind of imaging. In this case, we started to do minimal images in MEG images. With MEG is, I think was MEG already mentioned here in any of the talk? So MEG, as you know, it doesn't have very good spatial resolution. It's not like fMRI, but it has very good temporal resolution. And what Laila and was led by Leila Isik. And what we've done here is trying to let subjects in the MEG recognize minimal images. And we took the electrodes from the MEG and trained a decoder. The decoder is trained to say whether or not the image contains, say, an eagle in this case, and we had various images. And the question is, we can follow the performance of the computational decoder that tries to say, now the image, now the electrode, the pattern of electrodes allow me to deduce that there is an eagle in the image. And we see that the decoder is successful at, you can see here, at about 400 milliseconds. This is late for vision. The initial bottom-up initial recognition is more like 150 or something like this. And we also get the same results when we do psychophysics, that in normal images, you can recognize them at, you can get good recognition after, say, exposure of 100 milliseconds followed by a mask. To recognize correctly at the human level, to get to the human level that we get with minimal images, you have to give enough time, which we suspect that enough time is to allow the application of the top-down interpretation routine. And it seems if you don't give enough time, then people degenerate and become deep networks, and you get the same kind of performance roughly. But this is all still unpublished and still running, and we need more subjects, and all of this is looking in the right direction and looking in providing support for top-down processing for this. And this, by the way, it's interesting methodologically because it's very difficult with real images. It's so rich and you get so much information already in the wave going up, and because of this redundancy that even if you make 20% error, it doesn't really matter because you have redundancy, you have multiple sufficient minimal images within any object and so on. So it's very difficult to tease out the effect of where exactly the top-down information starts, where do you need it, where exactly you fail if you don't have it. So we think you need it for this internal interpretation and for the correct recognition of minimal images. And here you can start seeing good signals in the MEG. It provides you sort of a tool that is pretty unique and allows you to do these things. So let me add with very informal thing, but where I think this is going, I think that when you look at difficult images like action recognition, that we discussed below, many things that we do depend not on sort of coarse label of there is a person there, or there is an airplane, or there is a dog, but really things depend on very fine details of the internal interpretation. And so if you can turn off what I think is the top-down part of class-specific top-down processes, I think that many of these fine distinction that we make all the time, and it's what vision is all about. Vision is not about giving coarse categories, will go away. And so these things will become more and more an important part of vision. Let me just look at this variability in action recognition, but let me show you some specific examples. This is something that confuses current classifiers, that in both of them it seems that the person is drinking. This was because there is, a person, there is a bottle, and the bottle is close to the mouth, so the person is drinking at this rough level of description. But obviously, here this person is drinking, this person is pouring, right? Here is something very different. Is this person drinking at the moment? Yes or no? No, why not? She's holding a cup, and it's not far, maybe on the way to the mouth. We know that she's not drinking, right? But why exactly not? And again, this is something that is picked up as drinking by many recognition systems, but something is wrong here. All of these things, these are different objects and different actions that the people are performing. This is drinking from a straw, this is smoking, and this is brushing their teeth. But this depends on, you have to go to the right location and decide exactly what's happening there. It's the kind of thing that we do all the time. Some more challenges. These are just sort of informal challenges to show you how we can deal with fine interpretation of details of interest in the image. What is this arrow pointing at? Sorry? Yeah, but above the bottle, there is something else there. Sorry, yeah. Fingers, right. Let's see, just playing this. What is this arrow pointing at? Zipper. Let's see, here are two challenging things. Here are two arrows. What is this one pointing at? Right, not next to the cup, right, the saucer. This is really challenging. Let's see if what is this one pointing at? tray, not so the tray, think about it, it's this, but you match it with this thing here in order to make sure, to know that it's a tray. It's not something that will be easily picked up. But I mean, I'm looking for difficult things which are a little bit challenging, and you say, I can get it. But this level of detail, interpreting the fine details in images in a top-down fashion happens all the time. Is this person smoking? Of course not, and we are not fooled by it, and we immediately zoom on the right things, and it really, all the information is here at the end of the, so on and so forth. I mean, we were looking at dealing visually with social interactions, understanding the social interactions between agents in the, and again, it's very difficult to do correctly, and it depends on subtle things. I mean, you can get something rough, okay, but for example, is this sort of an intimate hug, or is this just a cordial hug of people who are not we know exactly what's going on, right? And it turns out that the features are not that easy to get. This was picked up incorrectly by something that we designed for people hugging, and it's not very far from people hugging, but it doesn't fool us, right? They're not really hugging. On social interaction, we know interactions even between non-human agents. I mean, this interaction, is this a threatening interaction or a friendly interaction? What do you think? Yeah, right, I think so too. Anyway, I think that all of these things that we can do, and I think that vision is about this. It's not about looking at this room and saying that this is a computer and this is a chair. It's about understanding the situations and making fine judgments and interacting with objects. In fact, we're looking at, as a part of we're doing at CBMM, we're looking at the problem of asking questions about images. So we want a system that you can give it an image and a question, and then we want the system to be able to process the image in such a way that will give you a good answer to the question. And this is interesting because it means that it's not just a generic pipeline of running the image through a pipeline, sort of fixed sequence of operations, but depending on what you're interested in, the whole visual process should be directed in a particular way to produce just the relevant answer. And we looked at a set of, with a student, we looked at a set of some 600 questions that we gave people on the mechanical Turk images, and they say, imagine some questions about these images, ask some questions about these images, and they came up with some images. We looked at them, and an informal observation, initial observation, is that most of these questions that people invented to ask about images, you needed some things which depended on precise internal interpretation of the details. So it's things that come up all the time. You have to dive into the image and analyze the subtle cues that will tell you that these are not hugging, and this is not threatening, and this is not an intimate hug, and so on and so forth. And this is what we are, the whole story of the minimal images and the internal interpretation is the real goal eventually is to be able to identify the important visual features and structures which are important for this, and thinking about the automatic learning of the how to extract the internal structure that will be support the interpretation of all these interesting and meaningful aspects of images that at the moment we do not have. So, okay, let me skip this. Okay, I think I've said all of these conclusions already in the final comment. So let me stop here.